there is any difficulty, then I can take up the questions even in between. There will be no problem. Okay.
Okay, sir.
So yes. So this is how this whole talk is organized, and we begin with the emphasis on just one second. Yeah, let me just turn off my video. Okay, so we begin with the emphasis on the point that mathematics usually it is taught as an abstract science. However, it is beyond abstraction. Okay, it is helping the mankind. One can look at the work of Ronald Ross, which was on malaria model. So he was the first one to basically, you should look at the story, and he was the first one to identify that there is a bacteria which is present in a mosquito, and that bacteria basically was present in the mosquito who has bitten an infected individual with malaria. And he established that this is how the malaria is being caused or spread in India. At that time, he was posted somewhere in Andhra Pradesh. So later on, he has given his entire theory and then the analysis and the models and everything. And then it's very well known that he also got the Nobel Prize. There is a very famous RSA algorithm which is very different and which is used for the security, for secure transactions or secure, messages transfer from one end to the other end. There is a very famous Black-Scholes model which is used for mathematical finance. Although that model, when it was given, it was relatively simple to predict the prices of the stocks and other commodities. Now things have developed a lot, and these are some of the examples where these people have won the what you can call is the highest literary prize, that's the Nobel Prize. These have won. So there are others also, but these are a few examples which I think people can correlate. So essentially, there are applications in all areas of knowledge, be it public health, be it management, be it epidemiology, which I will focus today, industry, economy, sociology, psychology, name the area, and then you can find the application of mathematics. However, the mathematics might be different. The kind of mathematics which can be used, that might be different. Mostly we are focusing today the differential equations only, and that too in a setup of infectious diseases. So when one is working on the interface of uh, any kind of domain, one needs precise methodology, and that precise methodology is provided by mathematical modeling. Why that is important? Because the mathematical modeling basically uh, has emerged now as an important tool, and we see that even during the COVID times, we were using it for predictions and for other kind of, control mechanism, how to control, and all those kind of things were discussed, and they were taken out of the mathematical modeling. The reason being that the alternative mechanism can be explored in order to understand the system better. And this is a very well-known fact that this is reasonable because you don't have to resort to the costly or ethically impossible experiments you many times which you cannot perform. Moreover, the models provide you the quantitative predictions as well as qualitative insights. So you can also get the numbers if you want to get the numbers, and otherwise, if you want to get the qualitative behavior, then also you can. And one most important part, since we work on the theoretical models and not the empirical models, is that we are more into the causation than correlation. Because in science, we need not only to understand the pattern, but also we want to understand why those patterns arise. So that why is answered via these mathematical models. So basically, what is a mathematical model? I will not get into the deeper details of this. I will provide this slide as the organizers have requested. So basically, it's a representation of the real world system, and it's a relevant representation of the real world system, which is in certain form of, you can say, abstraction, and that abstraction is represented via that model. Uh, so that model, since mathematics has blessed us with the numerous tools such as differential equation, stochastic process, algebraic equation, so on and so forth. I mean, depending on one's understanding, one can apply that tool and provide a model which is referred as a mathematical model. In essence, mathematical modeling is both art and science. It's an art to find a very good model, and it's a science to provide that the repetitiveness of those outcomes from that model. So it has both the aspects of the art and science in mathematical modeling. This is how a simpler process via mathematical modeling can be understood. Is that given a real world problem, we approximate that real world problem into a real world model. Then we plug in the abstraction, symbolic representation, etc., and we get the mathematical model. And from that mathematical model, we draw the conclusions, and then we compare it via the real world, and then we see whether our conclusions are matching or not. And then we finally say, very well, my model is good or bad, or my model is close enough, or for that matter. There is a very nice saying that all models are wrong, but some are useful. So this is what happens. Essentially, you cannot have a perfect model which will represent everything, because it depends on the modeler, that what modeler wants and what is the goal of the problem. So sometimes you may have a different model, and because your goal for studying a physical problem might be different than another person's goal, and therefore the two persons might get a different model. So you cannot say that my model is better than theirs model, and therefore this should only be used. I mean, it one can claim that one, but uh, that doesn't look that reasonable, because every model is basically the approximation of the real world. On the other hand, every model should be the approximation of the real world, because if you are completely modeling the real world somehow, although that's not possible, but if you are completely modeling the real world somehow, then there was no need of the model, because the real world was already there. The real world was already behaving. You did not need to have a model for that. So we do need a model, because we want a representative of the real world, not the real world itself. And therefore there should always be approximation, and there should always be, kind of error in the model. So what do we need when we are into the process of mathematical modeling? We need a detailed knowledge of the physical system. So today we will talk about the biological system. We'll see how these things work. We need a tool, mathematical tool, to comprehend this system. For us, it will be differential equations. We need to understand the analysis of that mathematical tool, and we use the theory of stability. We need to have results validation and improvement aspect there. For that, we will need some kind of parameter estimation, or we can see that how to correlate these with our existing real world, which is already there. So the important question will be which way of modeling will be the best, whether it will be theory driven, whether it will be data driven, or whether mixed. Again, it depends on the question which you pose. If you have a theory, you can get a theory driven model. If you have data, then you can have a data driven model. If you have enough data which is coming from the experiment, then you can have a data driven model. And sometimes you have a theory and then the data is already there, so you can propose both the data driven as well as the theory driven. The point here is, in order to have a representative of the real world system, uh, one should be very cautious. One should impose the conditions and restrictions of the system, and one should also be careful with the outcome of the model, and that should match with the real world outcome. So the caution must be there. Whichever process one wants to follow, one can follow. There is no problem. Only thing is that should be having some kind of relevance with the real world system. So these are some of the steps through which one should go for the modeling, as I have already discussed in the graphical representation. I will not be repeating this one. And these are some of the areas I would have probably spent some time. But today we'll be only referring to the models in the public health, which is our infectious disease model. So what are infectious diseases? First of all, we must understand, as I mentioned earlier, when you are trying to model a system, you have to understand the physical system. Okay. So when you are modeling infectious diseases, you have to understand what are the infectious diseases, how they spread, how they are caused. Uh, these this information must be there, because then the modeling process, modeling scenario, that will change. So infectious diseases usually are caused by pathogenic microorganisms such as the bacteria, viruses, parasites, and fungi. For example, viruses give rise to diseases such as human immunodeficiency virus HIV, influenza, SARS, recently COVID-19, measles, etc. And the bacteria give rise to diseases such as tuberculosis, anthrax, salmonella, chlamydia, cholera. That's very interesting. One of the interesting diseases, cholera, and some of you get beginning their journey of mathematical modeling. They should look at the spread of cholera disease in London, and how John Snow understood that how the cholera is being spread. Before John Snow, people did not know that the cholera is spread via contaminated water. So if you get some time, you just look at the internet and or some places and see that how John Snow has tried to understand by finding out or pinpointing using scientific study, pinpointing that cholera is spread via the contaminated water. It is spreading in the people who have drank the water from a particular pump, water pump. And protozoa give rise to diseases like malaria and trypanosomiasis, or it's also known as sleeping sickness, which is basically caused by a fly known as CC fly. So here we have already mentioned that how these diseases usually spread from one person to another. So some diseases spread from an infected person to the healthy person in direct contact, and some diseases they spread via some kind of indirect contact. That means there can be a vector or any other mode of transmission. For example, you see the respiratory droplets mentioned here in case of measles, or even in COVID-19, it was disease which was via respiratory droplets, or what airborne disease was there. Body secretions, for example, in case of chlamydia, biting of a fly, which is known as CC fly, in case of trypanosomiasis. So here there is a vector, there is another species which is involved in the transmission of the disease from an infected individual to the healthy individual. Mosquitoes, very common. We know all malaria, dengue, and all these diseases, they are spread by mosquitoes. And why do we need to understand all these things? Because once you understand that how disease spread, then only your control mechanism can be provided. Like contaminated water gives rise to disease like cholera and so on and so forth. So depending on the mode of the transmission, that how a disease transmits, as well as the fatality. Suppose if disease is not fatal, you probably won't bother about the disease. So depending on the mode of the transmission and the fatality, we usually assess the severity of the disease. So why do we do that? Because we need uh, either to control the disease or to eradicate the disease. So in order to do that, we need an in-depth understanding of the pathogen as well as epidemiology of the disease. What are the potential impacts of the diseases? Infectious diseases are leading cause of mortality and morbidity, deaths, and their related impacts. They contribute around 1/6 of the total deaths worldwide. So this is important to control them. They have serious socioeconomic consequences related to healthcare, travel, employment. We all have seen this during the COVID-19 period, and therefore there is no need to emphasize them more. And therefore, the control interventions, they are needed. However, it's very easy to understand that even if the control interventions are available, they may not be available for everybody. Or even if you have the availability of those interventions, there is a cost. There is a cost which is related with those control interventions, and therefore one must understand that that how to apply those control interventions so that the cost can be minimized. This means this also affects the public budget, and this affects the policy of the organization or the government. What are the in general, what are the control interventions? One among them is treatment, other is vaccination, other is screening. I think all these things we all are aware of. Fourth one is isolation or quarantine. Or so this is a non-pharmaceutical intervention, screening, isolation, and quarantine, and then awareness or information-induced behavioral changes. So these are some of the interventions which one can imply. There can be other interventions as well. And after applying these control interventions, the disease may slow down or may be even eradicated. All these interventions have their own importance or advantages and disadvantages. Via mathematical modeling, we address some challenges, that what should be the suitable control intervention policies, whether one should prefer the prevention or treatment, whether how should we apply the interventions, which of them should be given a more importance over the other one, and so on and so forth. So all these things one can address via mathematical modeling, although I will not be discussing all these points today, but all these things can be done, and these are the currently these are the important and interesting questions which researchers are trying to address. So usually we divide, whenever we are modeling, we use the compartmental model, and for that we divide the total population into subcompartments. We divide them into subcompartments, and these compartments are referred as susceptible compartment, or where the people who are susceptible to the infection. Then infective compartment or infective population, where we have the individuals who have caused the who have already gotten the infection, and then the third one is recovered population, where these are the individuals who had infection in past, but they have recovered from the infection. So these are the three partition, which are you can say important partitions, which are important partitions when you are doing the modeling. However, there are other partitions as well, and one can do more partitioning. For example, depending on again the status of the disease, one can do more partitioning. For example, vaccinated individual, for example, symptomatic infected individual, asymptomatic infected individual, so on and so forth. I mean, you can do as many partitions as possible. Why do we do these partitions? The point here is we do this partition because we want a clear-cut boundary among the population, okay, among the partitions in the population. We should not have a confusion when we are modeling whether the individuals from one section of the population, whether they can be in one section or they can be in another section or they can be in both. That kind of confusion should not happen, and that's the important message for partitioning. Okay, so we do this compartmentalization and we make the boundaries clear, and just in order to make the boundaries clear, we consider these kind of compartments. So susceptible means the individual who has no infection at the moment. Infective means the individual who is possessing the infection at the moment. Recovered means the individual who had infection in the past and is recovered now, and he may or may not spread the disease again. Okay. So sometimes in some cases, infected individual also considered as exposed individual. That means the individuals who are exposed to the disease, but they are yet to be infectious. They are not spreading the infection, but they can be infectious. So this is usually mentioned as susceptible, exposed, infected, recovered. So it's like, compartments of the train. People are moving from one compartment to the other compartment to the other. So susceptibles, once becoming exposed to the disease, they move to the exposed compartment. Exposed compartment move to the infected compartment, and finally the infected compartment become recover and move to the recovered compartment. So there is a flow of individual from one compartment to the other, and in most of the cases, this is the forward flow always. Some assumptions we have plugged in so that there should be clarity when we are considering the model. So the assumption which we are considering is that the disease is transmitted by the contact, which is a direct or indirect between an infected individual and susceptible individual. It means there is no other route of transmission of the disease, only via the contact of susceptible and infected individual. There is no latent period. What do we mean by latent period? Probably I will discuss it a little bit more, but later. But what do we mean by latent period is that once the disease is contracted by an individual, the individual immediately becomes transmitter of the disease. So receiver immediately becomes the transmitter of the disease. That means every individual who catches the disease, there is no kind of what you can call the incubation period is involved. That there is directly we are considering that there is immediate infection which is occurring. Okay. And we say that all susceptible individuals are equally susceptible. However, in realistic life, realistic scenario, this is not true, but we assume that they are equally susceptible. There is no differential susceptible, and therefore every individual is considered into single class. We also assume that the population is large enough to take care of the fluctuations or the stochasticity, and therefore our model is deterministic differential equation model. And in certain cases, we consider that the population and concentration is close. That means the population has fixed size. That means the total population is fixed at any given time. It is not changing, which can also be reasonable for the cases when you are considering for a shorter time period. So suppose if you are considering a model for 3 months time period or 4 months time period, then this assumption is reasonable. So very basic fundamental construction of the model susceptible to infective. This is referred as SI model. If you consider beta here, this beta as average number of contacts between the susceptible and infective. So imagine a situation that people are mixed up there and only susceptible and infective are there in the population. And if we just consider the number of contacts which susceptible and infective can have and take the average over all the infectives, then beta will be that average number of contacts per susceptible per infective. Okay, so that means suppose if there are 10 susceptible and 5 infective, and these people are mixed up in a population, and they have let us say 200 contacts, total 200 contacts in a unit time, some time, let us say 1 day or so. So the total number of contacts you count, and let us say it is 200 contacts. Then what you will do is that since susceptible were 10, infective were 5, that means in this case, and the time period is 1 day, and that means in this case the beta will be actually 4, because 10 into 5 into 4 equals to 200. Okay, so the average number of contacts, that's how. So every total contacts for 200, it might be possible that some susceptible might have made more contacts with the individuals. However, you are considering only the average number of contacts. Okay, because you are averaging the things, and that's how you have to plug in the things into the picture. Otherwise, you have to go for the individual based model. So beta is considered as the average number of contacts which a susceptible individual makes with an infective individual. So in that analogy, one can very easily understand that beta Si delta T is the total number of infection, uh, which is coming up there via the contact. So as many as susceptible are present there, as many as infective are present there, the number of infected individual will be proportional to those individuals, and that is our assumption also, right? That the disease is transmitted via direct contact or indirect contact between infected and susceptible individual. So this is how the total number of new infections are being counted. So these things are correlated, the number of new infection and the infection rate. Later on, this beta will be mentioned as infection rate. Okay, that means per unit time, how many individuals are getting infected. So that is correlated with the parameter beta here. So beta Si delta T, please remember this term. These are the total number of, you can say, the contacts which are made by susceptible and infective, and which also resulted in the successful transmission of the disease from infective to susceptible. And therefore, this is basically the number of new infection in the population. So these are the new infection in delta T unit time, and therefore, if you want to count the susceptible individual at the time, at the forward time t plus delta t, that will be equals to the susceptible individual at the time at time t minus the new infection which has occurred. So those new infection which has occurred, they will be removed from the susceptible population. So that is minus the number of new infections which have occurred in delta t unit time. Similarly, the infective at time t plus delta t will be equals to infective at time t plus the additional infection which has already occurred, and that is added up here. Now, with the help of these two expressions, one can write by using the calculus, one can write these two differential equations. One is ds over dt is equals to minus beta si. Another one is di over dt is equals to beta si. As I mentioned earlier also, and I can show you here also, I said that the population under consideration is closed. That means the population size is fixed. One can easily see here that ds over dt plus di over dt, which is right hand side, if you add up, that becomes 0. So that means ds plus I over dt equals to 0. That means the rate of change of sum of the population is 0, which means that the rate of change of total population is 0, which means the total population is constant. So susceptible plus infective is constant, and assume that the susceptible plus infective at any given time is equals to, say, n0. So if s plus I equals to n0, then we can also write s equals to n0 minus I, and that is what we have written here in the second expression. Di over dt is equals to beta. Instead of s, we have written here n0 minus I into I. This is a what you can call is that the expression which is a non-linear equation, and this can be very easily solved. It's not a big deal to solve this one. Sometimes it's referred as logistic expression or whatever you want to refer it as, but it can be very easily solved, and the exact solution of this equation can be found. However, we are not interested in the exact solution. Rather, we are interested in the pattern of the disease, and we want to understand that pattern from here. There are a couple of questions which I should address here. That why should I consider one equation? The answer is simple. If the information, total information, can be extracted from one single expression, then why do you need to have two expressions? Because one expression is sufficient, because the total population is constant, and therefore just studying one variable will be more than sufficient for us. So this expression, now we will plug in certain kind of more assumptions to make use of this equation in a better way, and try to show that even this simple equation or this simple model can give you meaningful observation or meaningful result. So what we will do is that we will say that in the beginning, when population is large and infection is just spread in the population, then the initial infective population is relatively small. Which essentially means that this n0 minus I, this term will be approximately equals to n0, and therefore what you can do here is that you can write this expression here. that in the initial phase of the infection, this di over dt will be approximately equals to beta n0 it. Beta n0, since n0 is the beginning population, it will be more or less constant, and therefore beta n0 can be considered as another constant, and this can be written as di over dt is equals to ait. This is a very simple expression. It is equals to I0 e raised to power at. This will be the solution. A is a constant here, not a matrix here. A is a constant parameter here, and this is the solution of this expression. You all know that this is exponential solution. You can all plot this one and just plot this one. And so what we have done here, and understand the claim here. Understand the claim here is that this is happening when the infective population is very small. When will be the infective population very small? Whenever there is a beginning of a disease outbreak, and that is what we have done for the case of COVID-19. So this is the COVID-19 data of 2020, March 2020, 20th March 2020, 22nd March 2020, and then so on and so forth up to 15th April. So this is like 20th March to 15th April, almost 30-35 days data is there. Sorry, almost 25 days data is there, and this is what is the data which was there, and you can see that that for the value of a is equals to 0.155, this data is very nicely fitting with the pattern of the disease. So the answer, I mean, again, as I mentioned earlier, when you are modeling, you don't need a very sophisticated model maybe at the very beginning, that that in the beginning that how should you predict. Even this very simple looking model can give you the predictions, and it can give, I mean, observation. On the basis of the observation, it can give you the prediction. However, after some time, you can see that the model predictions will be deviated from the actual outcome, which is when you read more models on COVID-19, you will realize why it is happening. Because later on, once the disease starts spreading, the precautionary measure, people will start taking precautionary measure, and because of that, the parameter beta will be impacted. The average number of contacts will be reduced. People will get isolated or quarantined, and all those kind of interventions will start happening, which were not considered in this model at all. And therefore, this will not be realistic. This model outcome will not be realistic, and therefore definitely there will be deviation of the curve from the real world. So further, in order to improve the idea, because the previous model did not consider the recovery of the individual, but naturally everybody gets recovered, or either gets recovered, or if the disease is fatal, then some of them might die. So must be considered the condition when the assumption is that everybody gets recovered. Whosoever gets the infection gets recovered. It's like simple cold, common cold which people get, that you will get cold and after a week time you will get recovered. So the differential equation in this case can be written as rate of change of susceptible is equals to minus beta si, plus there is another term which is gamma I. From where this gamma I is coming? This is coming from this expression di over dt is equals to minus gamma I. That means the rate of this is the negative rate. So there is a reduction in the rate of infective population, which is proportional to I. Which simply means that if you again go to the analogy of gamma I delta t, so gamma I delta t are the number of individuals who are recovering in a delta t time period, and then they are leaving. Since they are recovering, they are again becoming the assumption is that they are again becoming susceptible. Those who are recovering, they are not recovering permanently, and they are again becoming susceptible. So since they are again becoming susceptible, they are joining back the susceptible class. So gamma I delta t joining back the susceptible class, and once I divide by delta t and take the limit as delta t tends to 0, I get this kind of differential equation. All right. Now again, from the second differential equation, one can easily see that we can write that di over dt is equals to beta s minus gamma times it. And note that whatever is written here, note that di over dt is positive if beta s by gamma is bigger than 1, and di over dt is negative if beta s by gamma is less than 1. In fact, this is very important quantity in epidemiological system. So when this S is at the initial value, then it will be when, that means when the population is completely unaffected by the infection. At that time, we measure this quantity beta S by gamma. So at that time, S will be the total population N0, and therefore this number beta N0 by gamma. So this beta N0 by gamma in the very beginning, you can easily see that if this number is less than 1, then di over dt is negative. Di over dt is negative means what? The rate of change of I will be negative. That means I will be reducing. And di over dt is positive means what? That I will be increasing. So infective will be increasing if this quantity is larger than 1, and infective will be a decreasing number if this quantity is smaller than 1. Which means that whether the disease will survive or disease will terminate depends on this quantity, whether this number is larger than 1 or this number is smaller than 1. So we refer this number on which the disease dependent. We refer this number as what we call is basic reproduction number. And this basic reproduction number basically gives us the idea whether the disease will survive or disease will die out. Now, in earlier case, we assume that every individual who is recovering is becoming healthy. However, in realistic cases, sometimes, for some diseases, it might not happen. And the person may become immune permanent, like forever he is immune. For example, the diseases like chickenpox, if you are infected with one variant of chickenpox, you will not get it again. So the immunity is permanent, and therefore we offer another class of individuals there. After the susceptible and infective, we refer them as recovered individuals. Recovered means those individuals who had the infection, but they have recovered. In this case also, we have written in the similar fashion. We have written the rate equations, and we have observed that here also the basic reproduction number plays an important role, beta N0 by gamma. And now we will interpret this basic reproduction number in the sense of this information which we said earlier. So what is this beta Si delta T? I asked you to remember this one. What are these? These are the new infections. If you remember, I called them as new infections. These are the new infections, beta Si delta T in the delta T unit time, when the susceptible population is S and infective population is I. So now if I put IT is equals to 1 here, susceptible is equals to N0 here, and delta T is equals to 1 here. Look at this. Then in that case, you can compare this. So beta is beta, ST is actually your N0, IT is 1, and delta T is 1 by gamma. Okay. So this basic reproduction number now refers as that the contact rate out of one infective individual when the total susceptibles are N0, then in delta T unit time, that is 1 by gamma unit time, these are the total number of infections. Beta S I delta T. Beta is beta, S is N0, I is 1, and delta T is 1 by gamma. So during 1 by gamma time period, these are the total number of infections generated. Now we have to understand what do we mean by 1 by gamma. So in order to understand 1 by gamma, we write this infective equation for the recovery rate in this fashion. Di over dt is equals to minus of gamma I. As I told you that this is the recovery. So what do we mean by this equation? Di over dt is equals to minus gamma it. It says that the rate of change of infective is proportional to the infective population. Very clearly written here. Rate of change of infective is proportional to the infective population. This equation tells that per individual, if I divide this whole equation by 1 by I, then di over dt, 1 by I, di over dt is equals to minus gamma. So this says that per individual, the recovery is gamma in unit time. Di over dt, 1 by I, di over dt. So in unit time, the recovery is gamma, which means that out of I individual, gamma I individuals are recovering in unit time. Out of I individuals, gamma I individuals are recovering in unit time. And therefore, out of one individual, you will put the unitary law here. Out of one individual, gamma individual will recover in 1 unit time. You have divided I in the first and second term. And therefore, out of one individual, the one individual will recover in how much time? 1 by gamma. So in the second and third term, we have used the unitary law. So finally, out of one individual, the one individual is recovering in unit time, in 1 by gamma unit time. That means the individual is getting recovered fully. So if the rate, if gamma is the recovery rate, then 1 by gamma is the time period in which one individual will get recovered. That means this is the recovery period. That's what I want to convey from this slide, that if gamma is the recovery rate, then 1 by gamma is the time period of recovery. Okay, and this can be analogy can be actually further put for many parameters which are there. So if gamma is recovery rate, then 1 by gamma is the recovery period. Now come back to this point again. So beta n0 1 by gamma. This means that during the recovery period, these are the total number of infected individuals which are generated from one infected individuals in a totally susceptible population, and that is what is referred as basic reduction number. That how many infected individuals are created by one single infected individual in a completely susceptible population, and that's why this is referred as basic reduction number. We have simulated some of the systems for certain set of parameters. For example, beta is equals to 0.00. I thought that I will be providing you, showing you all these codes, but later on I thought that it might not be possible for me to do that, and therefore I thought that maybe some other time we will do that. So beta is equals to 0.003 we have taken, and gamma is equals to 0.05. And both SI and SIS model are simulated. R0 is found to be 4.08, which is bigger than 1 in both the cases. So in one case, you can see that the susceptible population is going down. This is the case of SI, and the infective population is getting larger and larger and larger, which is reasonable because from susceptible is reducing. DS over dt is negative and di over dt is positive, and therefore this is happening. In this case, this is SIS model, and therefore the susceptible population gets saturated to 1 point. Sorry. Gets saturated to 1 point, and the infective population also gets saturated to 1 point after some time. So there is a equilibrium of susceptible, because susceptible becomes infected, infected becomes susceptible again. So there is a equilibrium established when this kind of thing is happening. What is important here for the set of parameters which you are considering? You can look at this one. So this is the SIR graph. This is the graph for SIR model. This blue is your susceptible population, which is going down. I is the infective population, which is initially increasing, reaches to a maximum and then going down. R is the recovered population, which is increasing, and then keeps on to increasing and settles to somewhere. So what we did is that we wanted to understand the infective population, and therefore we plotted the 3 different graphs for the infective population. This is how one should interpret. Okay. So impact of the variation of the parameters on the second graph can be easily seen. The blue curve, the bottom one, the last one, the blue curve is showing that in this case beta is 0.003 and gamma is 0.05. Okay. So smallest beta and largest gamma we have chosen for this blue curve. And for this curve, this orange curve, not orange, this is, I think, sort of red. Okay. So this red curve is that beta is chosen to be 0.04. So beta is largest for this curve. This is 0.04. However, the gamma is chosen to be 0.05. So gamma is also large and beta is also large. And for this curve, beta is chosen to be, this is orange. For this, we have chosen beta to be 0.003 and gamma to be 0.004. So let us compare them one by one. Beta 0.04, beta 0.03, beta 0.03. So what you see, as you increase beta, that means you are increasing the infection rate, which means the number of average contacts increasing. What is happening? The peak is reaching earlier. Not only it is reaching earlier, but it is larger peak. Okay, the peak is larger. So larger as well as earlier. So if you increase the infection rate, then the peak will be reached to earlier and it will be larger. Whereas if you decrease the infection rate, beta, decreasing the beta will cause in reduction in this is also reducing the what you call is that the peak of the infective population, as well as it is increasing the time when the peak is achieved. So it means that reducing the contact rate directly impacts to the maximum infective. If nothing, no control intervention is applied, then also it reduces the time when you reach to the peak, as well as it reduces the peak. And then you compare this orange curve and then the blue curve. If you compare the orange curve and the blue curve, in this case the beta is same. Okay, in case of orange and blue curve, the beta is same. That means infection rate is same. However, in case of the blue curve, the gamma is 0.05, which means recovery rate is larger. But in case of orange curve, gamma is 0.04, which means recovery rate is smaller. So if the recovery rate is smaller, you can see that the peak is larger. So if you are providing more treatment or you are making more people recovered, then you can see that the peak is coming down. So peak is coming down with the recovery, and also the peak is delayed because of this infective, what you call is that beta, smaller beta. So if you reduce the beta and increase the gamma, then you can reduce the infective population, and also you can increase the time when the peak will be obtained. So these interpretation can be used, and they can be applied. So here we have so these were very basic models which we have considered. Now here we have improved this model further to include the birth rate, that means population natural growth rate of the population, the death rate of the individuals, and the disease related delta. Delta is the disease related death rate. So this is also included into the model system, and this is what SIR model is considered. Now one can apply the basic tools of the differential equation, and in order to analyze such kind of models, whatever we have done earlier, that can also work. One can write this, I mean, beta s minus, that way one can look at this equation that di over dt is bigger than 0 or di over dt is less than 0. If these numbers are bigger than, that means the basic reproduction number can be observed from here. But when the model becomes complicated, we don't usually find the basic reproduction number like this. Sometimes we use the eigenvalue approach, and sometimes we use another method, which probably I will be just discussing. So I will show you the eigenvalue approach. So for that, what we do, we consider this and simple SEIR model, a susceptible, exposed, infective, and recovered model. And in this case, we find out the disease-free equilibrium. What do we mean by disease-free equilibrium? We mean that the point or the solution where these rates are equal to 0, that means ds over dt is equal to 0, du over dt is equal to di over dt is equal to 0, and dr over dt is equal to 0. It's clearly written here. Equilibrium point x is equal to x star of a dynamical system, dx over dt is equal to fx, is called the equilibrium point if f of x star is equal to 0, which means dx over dt is equal to 0. So we equate all these equations to the 0, and then we figure out that for what values this will be 0. So it can be very easily find out that for I is equals to 0, E is equals to 0, and R is equals to 0, and lambda is and S is equals to lambda upon mu. This is your equilibrium solution or equilibrium point for this system. And then we apply the linearization. We linearize this this is a non-linear system because beta Si is present to product of two variables. So we this non-linear system we linearize. So we linearize it using the linearization technique. And what do we mean by linearization here? A linearized system around an equilibrium point x is equals to x star of dx over dt is equals to fx is given by dx over dt is equals to ax, where A is the Jacobian matrix. Okay, this is Jacobian matrix evaluated at the equilibrium point, or the that value x is equals to x star. Our claim will be that the behavior of the linearized system and the non-linear system is similar, and that claim is substantiated by this Hartmann-Grobman theorem, which says that near the hyperbolic critical point. What are those hyperbolic critical points? Those critical points for which you have non-zero eigenvalues. Okay, so near the hyperbolic critical points, the linearized system and the non-linear system have the same topological structure. So therefore, we can do for the cases when the eigenvalue is either having positive real part or negative real part. So we can very easily conclude that the linear and non-linear system are having similar behavior. What will happen to the cases when there is a either zero real part with the eigenvalue? Well, we cannot guarantee that from here. For that, we have to do further analysis, and that comes in the case which is referred as bifurcation analysis. Simply, we have mentioned here the stability. We say that equilibrium point x is equals to x star is equilibrium is of this dynamical system is stable, or sometimes we refer to as locally asymptotically stable if all the eigenvalues of the Jacobian matrix, they are having negative real part. Notice that negative real part. So we are not talking about anything of the other than the negative real parts. Okay, we just want to focus on the stability. So this stability idea we apply on this this system. We find out the Jacobian matrix and corresponding characteristic equation, and we can easily see the eigenvalues. All the eigenvalues, two eigenvalues can be easily seen from here are negative, and the other two eigenvalues will be given by this expression, which will be negative provided these two terms are positive, and this positivity of this term will be guaranteed if this number is less than 1, which is your basic reproduction number, which you have found already using this simple process. Sorry, not in this case. Not in this case. We did not do anything in this case. So this is actually observed here, because this case we could not find using that the idea or the thought which we are already using. Okay, so the basic reproduction number here can be easily found. Now the natural question arises: how do I know that this is a basic reproduction number? We can again write it in this manner: beta lambda by mu, k by mu plus k, and 1 by mu plus gamma. So this says that in 1 by mu plus gamma time period, the individuals who complete the exposed process, that means from exposed to infective, they become, this is the probability of becoming from exposed to infective. In a completely healthy population, these are the total number of infective in 1 by mu plus gamma time period. So the interpretation which we have done earlier makes sense here also, and therefore this is basic reproduction number. There is another way of computing basic reproduction number, which is using the next generation matrix method. In this case, what we do is that we divide the two kind of population. One is which is infective, another one which is not infective, and we write them in two classes. I will go through with the help of an example. You can refer to this particular paper if you want to read this one. This is from Mathematical Biosciences by Van Drisky and Watmo, and this paper, all this content is taken from this paper only. So you can write, you can figure out that the basic reproduction number is nothing but the spectral radius of the matrix which we will generate, which is referred as FB inverse. So what we do here, the same example which was taken earlier, the same example is taken here. In this case, we identify those populations which contains infection, and then we find out that what are the new infections which are generated in the population. Here one has to be very careful that what are the new infections. You should not count the same infection again. Okay, so you can easily see that the infection carrying population are E and I, and therefore E and I are considered as infection carrying population, and for them the rate equations are written, and these are written in this manner. These are the new infection and these are the other rates. So new infections, other rates. So we break this system dxi over dt as fi vi. So this will become our fi and this will become our vi. And then these are the corresponding Jacobian matrices of fi and vi with respect to the variables. So for example, here the variables are e and I. So with respect to e and I, these are the Jacobian matrix of fi and vi. And then we evaluate the FB inverse matrix. Why we do that? You can read the paper and you can understand that they will give you the number of new infective cases generated in each of the population. Okay, so each of the infective population, they will give you the number of new infection cases, which is coming from here that as the spectral radius, and this spectral radius is same as the basic reproduction number which we have generated earlier. So in some cases, it is very difficult to find out the eigenvalue, and therefore it is reasonable to apply this method and find out the basic reproduction number. And in some cases, it's actually not very, the computation is very, very complicated, and you may not be able to get it using the eigenvalue method, or the basic reproduction number which you get from the eigenvalue method may not be correct in the exact sense. if you go by interpretation. So in the basic cases, you will find that the things will match very simply. There will not be an issue. So this is how we apply and obtain the basic reproduction number. And this is the summary of whatever I have discussed here so far. And these are some of the books which I thought that, okay, those who are interested, when I will share the slides, you can look at these books. So this is one of the very nice books by Kushwaha Chavez. Even when I started my PhD, I read this was one among the very first books which I read that time. And this is a very nice review paper by H.W. Heathcote. If you want to get any kind of insight, then you should read this paper. You must read this paper if you want to have insight. These are very, recently I have seen these two books. They are very interesting books, and they are. Uh, I mean, this Castro Chavez, if you see, this is a thick book. Okay, but these two are, you can say, introductory in nature and very simple to read. Maybe within 15 days or 20 days, one can read the books. So these are the two simple books, and they give you a lot of information about disease modeling. This one, M.Y. Lee, is far more simpler, far more basic, at least in my opinion. And this Mayama Shobha, this may take you to little it will give you more exposure. So it depends on your choice. Uh, those many times I get this query: how should I find? The equilibrium point. How should I write the code? How should I write the solution? This and that. So for the basic knowledge, I will refer this book. Those who are interested, this book also contains a lot of MATLAB codes. So you should try those codes, you can understand them, and then you can apply them. So this book gives you the learning of differential equation with MATLAB codes, with mathematical biology examples. So this is one among those books where you can find things. And if you are not into the epidemiology and you are into the ecology, then probably this is going to be one of the most interesting books for you. There are many other books, but these are some of, you can say that, very basic book from where one should start, and if one wants to have some kind of exposure, then one can have it. So this is it from my side, and thank you.